Right. Today's session is on two very important properties of Fourier transforms: differentiation property and convolution property. So we'll try to cover these two properties in this session. Right. So before starting the session, so let me just introduce myself. So I teach these two subjects: communication systems and signals and systems. So if you wish to ask me any doubts based on these two subjects, you can post it in this Telegram group. This is my Telegram group. Right. So let's move ahead. So let me first quickly give you the answers for the homework questions that I've given you in yesterday's session. Yesterday's session was based on Raleigh's energy theorem. Okay, so these are the questions that I've asked. Right. So sine at by pi t, Fourier transform we know, which is a rectangle of omega divided by 2a. Okay. So if you shift it by 5 units, so this is like, if this is like x of t, you're talking about x of t minus 5 sine a t minus 5 divided by pi into t minus 5. We're talking about this. So Fourier transform will be e power minus j omega 5 or 5 omega into rectangle of omega divided by 2. So I'm expecting you to use two properties here: time shifting and Raleigh's energy theorem. Okay, so we got the Fourier transform of this signal. So finding the energy of this signal here, what is the question asked? We have to find the energy of shifted sinc function. Finding the energy of sinc function is very tough. So whenever things are tough, or whenever it is difficult to integrate, so you always have to think about there should be some property to make it easy to resolve. Okay, so if you give a thought about it, then okay, something is squared and integrated means that finding the energy. Okay, if it is difficult to find it in time domain, whenever something is difficult to find in time domain, it will be easy in frequency domain. Use some property. Similarly, if something is difficult to find in frequency domain, use some property so that you can find it in time domain easily. Right. So the energy, Raleigh's energy theorem, what it says is energy in time domain is same as energy in frequency domain also. So, but whenever you are doing integration with respect to omega in frequency domain, there should be always a 1 by 2 pi factor. Okay, right. Now let's find it. We want to find this. We are asked to find this, but using property, if you find this, it is as good as finding this. So we can write as 1 by 2 pi integration. If you apply modulus to this, modulus of e power minus j 5 omega, j is there, so that's why if you apply modulus, it will become 1 into rectangle of omega by 2a whole square. If you square a rectangle, what happens? It will still like a rectangle only, you know? Correct or not? So if you square a rectangle with a height of 1 unit from minus a to plus a, if you square it, it will become 1 square, it is again 1. So it will be the same rectangle and d omega, limits from minus infinity to plus infinity. And rectangle has an equation of 1 in the limits from minus a to plus a. So if you integrate, it becomes 2a by 2 pi, which is a by pi. That's it. Or if we think in a commonsensical way, then also we can find the answer much easier. Look at this one. This is shifted version, right? Do you think that energy will change because of shifting? Because of shifting, will the energy change? Will the area change? No, right? It will not change, no? Correct or not? If you shift this rectangle towards right side with 10 units or 20 units or 30 units, will the area change? Will the energy change? No, right? So if you have got that idea, then instead of this shifted function, take an easier function, sine at by pi t. Find the energy of this one by finding the energy of this, which is more easy to find. We could have saved a lot of time, some time at least half or 1 minute. If you have recognized that, okay, time shifting will not change energy. If you have realized that. If you have not realized, that's fine. It will take half or 1 minute extra. That's fine, but still we can find it. Next one. Next is an easy question. We are asking you to find the area of the signal. But if you want to find area, you have to integrate, which is tough to integrate the sinc function. Whenever something is tough to do in time domain, look at it in frequency domain. So area in time domain is equal to value at 0 in frequency. So they're asking us to find integration of x of t dt, which is same as x of omega equal to 0. In this case, x of t is sine 80 by pi t. In this case, x of t is sine 80 by pi t, and x of omega is rectangle of omega by 2. So we want this integration value is same as the value of the Fourier transform at omega equal to 0. What is the value of the Fourier transform at omega equal to 0? It is 1 only. That's it. So that is the answer. So the answer for the first question is a by pi. The answer for the second question is 1 unit. If you have done it, you can cross check if you have done it correctly or not. Okay. Right. Very good. So let's move ahead and let's go to the today's topic. So today's topic is on differentiation property and convolution property. So this differentiation property, what it says is if you do differentiation in time, how to find the Fourier transform easily. If you know a signal and its Fourier transform, if you know a Fourier transform pair, and if you do differentiation in time domain or in frequency domain, what happens in the other domain? That is what this property talks about. So I'll talk about what happens if you do differentiation in time and what happens if you do differentiation in frequency. Both I'll talk about. Okay. So that I put it in a statement. A signal x of t has a Fourier transform of x of omega. Let me write it. X of t is having a Fourier transform of x of omega. It means you know a signal and its Fourier transform. If you know that, then according to differentiation property of Fourier transform, differentiation of x of t, which means d by dt of x of t, differentiation of x of t has a Fourier transform of j omega into capital X of omega. See this one? So if you know Fourier transform pair, if you do differentiation in time domain, it's very easy to find the Fourier transform of differentiated signal if you know the Fourier transform of the original signal. If you know the Fourier transform of original signal, differentiated signal also has same Fourier transform, but a small change here, multiplication with j omega factor. That's it. So with the help of this property, if you know a signal and its Fourier transform, and if somebody asks you to find the Fourier transform differentiated version of whatever you know, then it will be easy to find. Okay, right, wonderful. So this is the differentiation in time property. Let me discuss some examples for this. Look at this one. U of t. Do we know the Fourier transform for this? Yes. It is pi into del of omega plus 1 by j omega. Let's test this property, whether it is giving it correctly or not, just for practice sake. D by dt of u of t. What is the Fourier transform of this one? According to the property, if you do differentiation in time domain, in the Fourier transform, which is the same Fourier transform copied multiplied with j omega. Right? Then copying this same Fourier transform, pi into del of omega plus j omega. My mistake. Fourier transform is pi into del of omega plus 1 by j omega. My mistake. 1 by j omega multiplied with j omega because of differentiation property. Differentiation in time, what happens in frequency domain? Multiplication with j omega. So what is the result? J omega multiplied with pi into del of omega plus j omega into 1 by j omega is 1. Look at this one. Whenever impulse is multiplied with any function in the neighboring function, substitute the location of the impulse. What is the location of the impulse? Omega equal to 0 is the location of the impulse. Wherever you find omega in the neighboring function, substitute with 0. So it will become 0 multiplied with del of omega plus 1, which is again 1. Come on, sir, I have seen this Fourier transform. 1 is a Fourier transform of a signal that I know is correct. What is d by dt of u of t? It is del of t only. Yes, we already know this Fourier transform. Correct? We're just trying to test the property here. Yes, it is giving perfect answers. So if they're asking Fourier transform of del of t, because we already know it, we can directly say it as 1. We don't need to don't need to use differentiation property here at least. Because somebody asks you differentiation of u of t Fourier transform, you know differentiation of u of t is del of t. So if you have done that, there is no need to do all this stuff, right? But anyway, this is one example. Okay, let me give you one more example as well. d by dt of e power minus a mod t. How about the Fourier transform of this one? So if you want the Fourier transform of this one, first write the inside function. If you know the Fourier transform of this, then only we can apply differentiation property to find it. Otherwise, we can't apply differentiation property. To apply differentiation property, the requirement is whatever signal is being differentiated, you should know the Fourier transform of that. And this is a standard signal which we have to remember the Fourier transform. There are 4 or 5 functions as I told you earlier. Step function u of t, you have to remember the Fourier transform. E power minus at into u of t, you have to remember. E power minus a mod t, you have to remember. And apart from these three, one or two other functions, sinc function, sin 80 by t Fourier transform is rectangle of omega by 2. All the remaining Fourier transforms we can get it using properties. So the Fourier transform of e power minus a mod t is 2a by a square plus omega square, right? Okay. Now if you differentiate in time domain, what happens in frequency domain? What happens is same Fourier transform copied, just multiplied with j omega. Multiplied with j omega. So that is the Fourier transform. So whenever you see differentiation in one domain, in the other domain, what happens? Multiplication of the j of variable happens. Differentiation in time domain creates multiplication factor of j omega in frequency. Fine, let's move ahead to the next one. Same differentiation property, but in frequency domain. So what happens if you differentiate in frequency? That same property is discussed here. X of, let's say x of t has a Fourier transform of x of omega, capital X of omega. Then according to differentiation property of Fourier transform, differentiation of x of omega, x of omega we have to differentiate only with respect to omega because the variable is omega, has an inverse Fourier transform of minus jt. See this one? Minus jt is the multiplication factor. I'll just write the time domain differentiation property also so that it will be easy to remember for you. If you do differentiation in time, what happens in frequency domain is multiplication with j omega. Whereas if you do differentiation in frequency domain, it is similar thing. J is there, variable in time domain is t, here variable in frequency domain is omega. J and variable both are common. Okay, but the only difference is if you are doing differentiation in frequency domain, then there is a minus sign extra. That is the only difference. Okay, integration in one domain, what is it doing? In the other domain, there's a multiplication factor of j times the variable. Okay, j times the variable is there when you do differentiation in one domain, and there is a minus sign extra whenever differentiation is happening in frequency. Hi Prakash. Okay, so let's do a question based on this. So here, don't expect someone to ask you minus jt Fourier minus jt is multiplied in time domain. What happens in frequency domain? Don't expect that. Okay, so this property we can also rewrite it as t times x of t. So sometimes they also call this as multiplication. Different names. People will keep different names for different properties, but the idea is same. Multiplication with time with t property. Multiplication with t property. Multiplication with t property. So if I send this minus j onto the other side, or multiply with j on both sides. If you multiply with j, j into minus j becomes plus 1. So it becomes j times d by d omega of x of omega. See this one? It's easy to remember. Multiplication with the variable in the one domain, what happens in the other domain? Differentiation happens. There is an extra j factor also. Similarly, differentiation in time domain, it is easy to remember in this format. This is more easy to remember. Okay, so we have discussed about what happens if differentiation is done in time domain or in frequency, both cases. I think you will not forget that anytime in future. Okay, let's do a problem based on this property. Can you find the Fourier transform of t into e power minus at into u of t? How about this? So I'm asking you to find the Fourier transform of this one. So t is there. You can look at it as multiplication with t property. So to apply this property, first of all, you should know the Fourier transform of the original signal to which t is multiplied. So let's take the basic signal that is available here. Let's find the Fourier transform of this one, which is 1 by a plus j omega. Okay. Now let's apply multiplication with t property. If you multiply with t in time domain, what happens in frequency domain? It becomes j times d by d omega of x of omega. So if this is x of t, this is like x of omega. So if x of t is multiplied with t, what happens in frequency domain? Differentiation of x of omega happens. So what is x of omega here? 1 by a plus j omega, which is equal to j times, let's differentiate this, is minus 1 by a plus j omega whole square into differentiation of the denominator part is j, just j. So it becomes j into j is minus 1, minus into minus is plus, right? So it is 1 divided by a plus j omega whole square. Look at this one. So that is the answer, right? Similarly, I can ask you one more question here. How about t square into e power minus 8t into u of t? How about this one? How about the Fourier transform of this one? Let's find it in the same manner. So let's look at it as t into e power minus 8t into u of t. Okay. Okay. So now on top of this one, we know the Fourier transform of this one. If you multiply with t, what happens? Again, j times d by d omega of 1 by a plus j omega whole square, which is equal to j times, the differentiation of this is minus 2 by a plus j omega whole square. Differentiation of the inside part is j. So j into j is minus, minus into minus is plus. It becomes 2 by a plus j omega whole square. Similarly, you can extend it multiple t power n is also there. That also we can do. Okay. So if it is t cube, what happens? Again, you differentiate. Then what happens is 3 again 3 will come. So if it is t power 3, it becomes 3 into 2. If it is t power 4, it becomes 4 into 3 into 2. It is like n factorial by a plus j omega whole power n. We can generalize that also, but we don't need to by heart these things. You just apply this property. Okay, fine. So that is an example based on differentiation property. If differentiation happens in frequency, or we can also call it as multiplication with t property. Right. Next, let us talk about the convolution property. If two signals x1 of t, x2 of t have Fourier transforms, okay. Before talking about this property, I'll give you one more example here. Can anyone tell me what is the Fourier transform of t into u of t? T into u of t. So, are you trying to apply the property of multiplication with t property? No, you should not apply, because what is t into u of t? You can recognize that it is r of t. For r of t, will Fourier transform exist? This is a neither energy nor power signal. For neither energy nor power signals, Fourier transform does not exist. If Fourier transform does not exist, what are you trying to find? If you try to blindly apply the formula, you get some junk thing which is not valid. So Fourier transform does not exist because R is a neither energy nor power signal. So before finding Fourier transform, when you are multiplying with t, what happens is just t is an increasing signal. So when you multiply with t with some kind of power signal, so for example t into sine t is also a power signal. For Power signals, they stay for infinite time. When you multiply with t, what happens is that t equal to infinity, this becomes infinity. Infinity multiplied with anything is infinity only. So that's why when you multiply t or t square with any power signal, what happens is it becomes a neither energy nor power signal whose Fourier transform does not exist. Mind this. Don't blindly apply the formula. Just try to understand if the Fourier transform exists or not. Generally, in a gate paper, they will not ask about Fourier transform which does not exist or which it does not exist. But in future, they might ask. We don't know. But that is the basic. There are signals which don't have Fourier transform also. So for them, we don't need to try to find them. What are those signals? They are neither energy nor power signals. Okay, right? Next. If two signals x1 of t and x2 of t, we talk about convolution property here. Convolution can happen in time domain or in frequency domain. So we're talking about what happens, what if convolution is happening in time domain. If two signals x1 of t and x2 of t, there are two signals x1 of t and x2 of t which have a Fourier transform of x1 of omega and x2 of omega. Second signal x2 of t is having a Fourier transform of x2 of omega. Okay. Then according to convolution property of Fourier transform, what happens is if you know two signals and their Fourier transform, then only we can apply this property. If you don't know the two signals and their corresponding Fourier transform, you can't apply this property, because if you don't know the signals and their corresponding Fourier transforms, then how can you apply this property? So if you know two signals and their Fourier transforms, and if those two signals are being convolved in time domain, if those two signals are being convolved in time domain, so if you want to find the Fourier transform of this convolved signal, then it's very easy. Because if you want to do convolution in time domain first, then it's a complicated integration process, which will take a lot of time. After convolving, you'll get some signal. For that, if you apply Fourier transform formula, it might take a lot of time. Instead of taking that much of time, if you apply convolution property, it is very easy. So if you know the Fourier transform of these two signals, you don't need to do the convolution. You don't need to apply convolution integral, get some result, and then apply Fourier transform formula. You don't need to do that. You can simply apply this property. What it says is, if you know the Fourier transform of two signals, if you do convolution time domain, just multiply the corresponding Fourier transform of both the signals. Whatever two signals are involved in convolution, take their Fourier transform of both the signals and just multiply. That result, product of the Fourier transforms. This result of product is the Fourier transform of convolved signals. Very simple property. Very, very simple. Very easy to understand. We can solve a lot of tough, tricky questions. They might look very tricky, but when you apply this property, it will look very easy. Right? Let me give you an example. Look at this one. Find the Fourier transform of e power minus at into u of t into convolution with e power minus vt into u. Let's say this one. Right. So first, let us take the individual signals. This is like x1 of t, this is like x2 of t. Whatever two signals are involved in the convolution, first take those signals and write the Fourier transforms of them. A plus j omega. Look at this one. Now, what are they asking us? They're asking us to find the Fourier transform of this convolved signal. When you do convolution of two signals in time domain, the Fourier transform of those signals is the product of the corresponding Fourier transforms. Take the Fourier transform of this, take the Fourier transform of this, just multiply. There's 1 by a plus j omega multiplied with 1 by b plus j. That's it. Okay. So I can also ask you one more question. Same format. Instead of asking to find Fourier transform of the signal, I can also ask you e power minus at into u of t, convolution with e power minus bt into u of t. What is the result of this? What is the result of this? Basically, if you want to find this result, you have to use integration formula, like convolution integral formula. x1 of t convolution with x2 of t. What is the formula for this? x1 of tau into x2 of t minus tau theta. We have to use this complicated formula, which will take a lot of time to resolve. It will definitely take minimum of 5 minutes to resolve this. If you want to do convolution of time two signals in time domain itself, then it will take time. Definitely, it is time taking process. Instead of that, why can't we apply convolution property? Compared to convolution, multiplication is very easy, correct? Right. So what I'll do is, so for these signals, we know the Fourier transform. So when they ask this, you have to keep this in mind. Okay, it's difficult to find convolution, but it is difficult. It is easy to find the Fourier transform of this total signal because we know the Fourier transform of this. We know the Fourier transform of this total thing. Also, we know the Fourier transform. We just now found what is inverse Fourier transform of this part. Inverse Fourier transform of this is this one only. So what if this is as good as, if you want to find this, find inverse Fourier transform of 1 by a plus j omega multiplied with 1 by b plus j omega. If you are able to find the inverse Fourier transform of this quickly, then finding the Fourier transform of this and then finding the inverse Fourier transform of this, it is more easier. Sir, if you find inverse Fourier transform, you get exactly this now. No, it need not be. It need not be. How? Let's see how. Okay. So if this is a complicated procedure, then you can go with direct convolution integral formula. See this one. Whenever they're asking us to evaluate convolution, always remember convolution can be easily done using Fourier transform properties or Laplace transform properties also. Whenever convolution is involved, in any problem, when they give you any problem where convolution is involved, there are a lot of ways in which you can perform convolution. Okay, directly you can use convolution integral, convolution basics only, or else you can take the help of Laplace transform. You can take the help of Fourier transform to do the convolution much faster. Okay, now they're asking us to find convolution. What we will do is we can find the Fourier transform, and it's easy to find the Fourier transform of this total signal. So let's find the inverse Fourier transform of this one. If you directly find the inverse Fourier transform, the inverse Fourier transform of this is this, inverse Fourier transform of this is this, multiplication becomes convolution in time domain. You might get this. But instead of that, what I'll do is I will apply partial fractions here. I will apply partial fractions here. So it is in the form of 1 by x plus a, 1 by x plus b kind of thing, right? So we'll apply for partial fractions. So if we apply partial fractions, what happens is, so what should we substitute? Omega with the minus ja, right? Omega with ja, yeah. Omega with ja, yeah. So if you substitute omega with ja, it is b minus a here. You can do partial fractions in the method that you know. I am doing it in my own method. So this is a minus b. Now let's calculate inverse Fourier transform. B minus a is just a constant. Okay, b minus a into what is inverse Fourier transform? 1 by a plus j omega. It is e power minus at into u of t plus a minus b into what is inverse Fourier transform? 1 by b plus j omega. It is e power minus bt into u of t. See this one? It becomes very easy. One my mistake. There's a small mistake I've done in finding the partial fractions. This b minus a is not in the numerator, it is in the denominator. Okay, so it is 1 by b minus a, 1 by a minus b. So now we can take 1 by b minus a common, e power minus at into u of t. Here it is a minus b, so b minus a is taken common, so it becomes a minus sign here. So this result is e power minus at into u of t minus e power minus bt into u of t divided by b minus. Is that okay? Is that correct? Cross check and tell me if there is any slight calculation mistake from my side. think that is correct also. Okay, correct. So that is the result. You can remember this result also if you can remember. Otherwise, we can get it from this in 1 or 2 minutes. Right? Like this convolution property helps us to find convolution of two signals also easy. When convolution of two signals Fourier transform is asked, yes, that we can do. If they're asking us to find the result of convolution also, we can find the Fourier transform of it and then do partial fractions and then find the inverse Fourier transform. You get the result of the convolution. Even using this procedure, if you do also, you'll get this. Okay, right. So that is convolution property in time. Next. So what about convolution property in frequency? So let's say x1 of t has a Fourier transform of x1 of omega and x2 of t has a Fourier transform of x2 of omega. Now they're asking us to find what if you do product in time domain. From the previous property also you could have understood. If you do product in frequency domain, it's convolution in time domain. Similarly, since Fourier transform satisfies duality property, if you do product in any one domain, in the other domain definitely it should be convolution. Convolution in one domain, product in the other domain. So now, since it is product in time domain, our common sense says that it should be convolution in frequency domain. That is what this property talks about. Yes, it is convolution in frequency domain. But here also we have to be careful. See here, convolution means there is some integration involved or not? Is there some integration involved? Convolution means definitely there is some integration involved. Whenever integration is involved, I told you that there is a 1 by 2 pi factor when you are doing integration with respect to omega. Since there is integration involved with respect to omega, that's why I am putting a 1 by 2 pi factor. Remember in that. Whenever there is an integration involved with respect to omega, there should be a 1 by 2 pi factor. So we have seen that in area property, Estes-Rayleigh's energy theorem property. Okay. And in convolution, if you're doing convolution in frequency domain, then also we have this 1 by 2 pi factor. But if you do this convolution in frequency domain with respect to f, there is no need of any 1 by 2 pi. So this result or this result both are same. Or we can also say it as if you do product of two signals in time domain, and if you want to find the Fourier transform of it, then it is convolution in frequency. But which is more easy? Product is more easy. Convolution is tough. So always they'll ask us to analyze this part, not this one. This part can be easily analyzed by finding the inverse Fourier transform. Because in inverse Fourier transform, it is just product, which is more easy to find. Okay. Fine, wonderful. So let's see an example for this. Find inverse Fourier transform of 1 by a plus j omega convolution 1 by b plus j omega. See this one, I'm doing convolution in frequency. I'm asking you to apply the property of product of signals in time domain or convolution in frequency. We can also call this property as convolution in frequency domain or product in time domain property. Name can be anything. Right. So to find inverse Fourier transform, first you should know the inverse Fourier transform of individual signals. Then only you can apply the property. So a 1 by a plus j omega has an inverse Fourier transform of e power minus at into u of t, and 1 by b plus j omega has an inverse Fourier transform of e power minus bt into u of t. Right? Now they're asking us to convolve the signals in frequency. They're asking us to convolve signals in frequency domain. If you do convolution in frequency domain, what happens in time domain? What happens in time domain? There should be a product in time domain. But whenever omega is involved in frequency domain, whenever convolution is happening in frequency domain, there should be a 1 by 2 pi factor. There should be a 1 by 2 pi factor. So that 1 by 2 pi factor should be there. So When you do convolution in time domain, frequency domain, along with 1 by 2 pi factor, what happens in time domain? Just multiplication, e power minus at into u of t multiplied with e power minus bt into u of. See this? Now, what is the result for this? It is e power minus at into u of t into e power minus bt into u of t. U of t into u of t is u of t only. Next, e power minus at into e power minus bt is e power minus of a plus b into t. See this one, how simple it has become. Multiplied with. They're talking about this function, but we don't want to 1 by 2 pi there. So send this 2 pi onto the other side. It becomes 2 pi times. Yes, that is the result. See, this looks very complicated, but when we have applied the property of convolution, it has become so simple. Such a simple answer. But if you want to do this convolution using convolution integral, it takes at least 5-10 minutes. So a lot of, whenever problem looks complicated, think of some property which might help you solve that problem easily. Okay. Right. I can also, there is one more type of question. Same question I'll also ask you like this. Find 1 by a plus j omega convolution with 1 by b plus j omega. Instead of asking you inverse Fourier transform of this one, I can ask you only find this one, find the result of this. So if you want to find the result of this, doing convolution of these two segments is complicated stuff. It takes time. So instead of that, you can use some property. Instead of convolution, multiplication is more easy. So instead of doing convolution in frequency domain, do multiplication in time domain, and then take Fourier transform again. Okay, right. So we know the inverse Fourier transform of this. We know the inverse Fourier transform of this one. See this one? It's very easy. We got this. We got this. So this is same as this one from the previous problem we've understood. This and this are same. One second. Yeah, there we're talking about inverse Fourier transform, right? Yeah, we got inverse Fourier transform of this one. So for this function, we know the inverse Fourier transform. So these two are Fourier transform pairs. These two are Fourier transform pairs. Correct? So how about you can find the Fourier transform for this one? Fourier transform of this is same as this. Correct? But when you try to find the Fourier transform of this one directly, you'll get a different result, which might be same as this. So that result is, so if you find the Fourier transform of this one, you get that result. And what is that result? It's 2 pi times, 2 pi is a constant, I'm putting it outside. C power minus 80 into u of t. Fourier transform is 1 by a plus j omega. Instead of a, we are having a plus b. Instead of a, we are having a plus b, so it will be a plus b here. So it will be 1 by a plus b plus j omega. See the result, how simple it is looking like. This problem, which is looking very complicated, with the help of convolution in frequency domain property, so we have found the inverse Fourier transform easily. That inverse Fourier transform, if you just simplify it, it will become a very simple function. For which, if you find the Fourier transform, you are getting the result of this convolution. Okay, I hope you're following. So wonderful properties. So you have to use it effectively. You have to use it properly. First thing is you should get the idea. Whenever you look at the question, you should get the idea what property can I use. In Fourier transform is all about properties. Whenever you see a question, you should get the idea of what property can I use. Okay, right. So let's practice some questions. Let's practice some questions before winding up the class. How about this one? Looking at this one, how do we get the idea? Just think in the same manner that I'm doing. So you might have seen 1 by 3 plus j omega. Whatever you know in that function, don't take the total function. Take only that part of the function which you know very well. And on top of that, we'll apply the properties. 1 by 3 plus j omega, we are familiar with it. It is looking like 1 by a plus j omega, whose inverse Fourier transform is e power minus 80 into u of t. In this case, in place of a, we are having 3. E power minus 3t into u of t is the inverse Fourier transform of only 1 by 3 plus j omega. But you want the square happening. But there is no property, no property as such where squaring is done in frequency. There is no such property. There is no such property in Fourier transform where squaring happens. So since there is no such property as squaring, think about some property which will produce squaring. For this function, if you want to have squaring in the denominator, what kind of property can do that? Okay, there is a property. Differentiation property is there. No, if you do differentiation of 1 by 3 plus j omega, is it possible to produce 1 by 3 plus j omega whole square? Yes. If there is no direct property that is visible, think of some property which can create that function. From this function, if you want to get this, what mathematical operation you can do? Think about it. So there is only one operation which can get this function from this function, and that is differentiation. So differentiation of this will give us 1 by 3 plus j omega whole square. Okay. So whenever squaring is happening, think about differentiation property. Okay, you know your function, and that function is being squared. They are asking us to find something about that function, squared function. Then you should get the idea that okay, differentiation is happening. They are using differentiation property. So when differentiation happens in frequency domain, what happens in time domain? Multiplication with minus jt happens. Multiplication with minus jt happens. E power minus 3t. That's it. That is the answer. So the answer for this is minus jt into e power minus 3t into u. Okay. Very good. Let's move on to the next question. See this one? I'll wait for a minute. Try this one. Same ideas. Same ideas. Look for some function which you know already. Write the Fourier transform pair of that function which you know already. Now for that function, think of some property or think of some mathematical operation which can get you that function they're talking about. Then you can apply properties. Okay. So if you want, I'll do a generic also. So what is the function that you already know? It is 2a by a square plus omega square is a function that we already know. Whose inverse Fourier transform? So we have seen this function in Fourier transforms. So this function we will get for a signal in time domain, which is e power minus a mod. E power minus a mod where a is a positive value. If a is negative value, this Fourier transform does not exist. Because if a is negative, then what happens is it becomes exponentially increasing. It becomes neither energy nor power. Yes, this function are looking close. They are not same. But from this function, how to get this one? See this one, squaring is happening. Squaring, there is no direct property on squaring. Okay, what other mathematical operation you can do to get this function? Okay, one idea. The previous slide also we have applied the same idea. Okay, differentiation might help. Just I'm not sure whether differentiation will help or not, but just have that idea. Okay, what other operation? If not differentiation, what else is there? Think about it. So let's apply differentiation and see. D by d omega of 2a by a square plus omega square. So it is 2a aside a square plus omega square minus 1 by a square plus omega square whole square into differentiation of this part is 2 omega, which is equal to 4a omega minus 4a omega divided by a square plus omega square. See this one? Yes, we got it. So this is looking similar to this, that a part is missing, that minus sign is missing. Apart from that, the constants we can adjust easily. But if there is no omega here, we can't do adjustment for that. We can't do adjustment for that, but we have to use some other, by using some other property, maybe differentiation in time property. By using that, we can get that extra omega also. That is also possible. But see this one, omega divided by a square plus omega square is exactly matching. So what is the inverse Fourier transform for this? So if you do differentiation in time frequency domain, differentiation in frequency domain, what should happen in time domain? Multiplication with minus jt. Multiplication with minus jt should happen. Okay. This implies this minus sign we can cancel on both sides. T into jt into e power minus a mod t Fourier transform is 4a omega divided by a square plus omega square whole square. Okay. Now that what is being asked here? 4 omega. See this one, this just constants outside can be adjusted, but constants inside we can't adjust. So a square should be omega 4. It means a should be 2. It means 4 into 2 into omega divided by 2 square plus omega square is 4 plus omega square whole square. I'm substituting a with 2. Don't substitute, sir. See here, 4 omega is there, which means a is 1. No, a is not 1 because a here in the numerator can be adjusted. But if you take a as 1, a is 1, here it should be 1 square, but it is not 1 square here. So whatever is the function which is inside, we have to choose carefully. A should be choose a according to the numerator part or the denominator part. According to denominator we have to choose, because if a is chosen as 2, in the numerator it is not 2, but the constants we can adjust as we want. Right. Now it becomes jt into e power minus a mod t. So this 2 is missing here. So 2 you can multiply and divide both sides. You can divide with 2 on both sides. The 2 gets cancelled. So 4 omega by 4 plus omega square whole square. Inverse Fourier transform is j into t by 2 to e power minus a mod t. That is the inverse Fourier transform. Is that okay? Wonderful. I'll ask you one more question as well. How about this one? So if you have not subscribed to the channel, you can subscribe, and if you like this session, you can press the like button. Fine. So let's find it. So inverse Fourier transform of this one. So this convolution is difficult to find. Instead of doing convolution, what we can do is we can do multiplication in time domain. Correct? We are supposed to ask, we are being asked to find inverse Fourier transform, right? So inverse Fourier transform, if you want to find this for this total function, if you know the inverse Fourier transform of this function and this function separately, then we can find the inverse Fourier transform of this total function also. What is the inverse Fourier transform of this part? The inverse Fourier transform of this part is, if you remember, this is e power minus a mod t. Fourier transform is 2a by a square plus omega square. That idea I'm gonna get, because this is looking like a square plus omega square kind of function. 2a is not there, so you can send the 2a onto this side. So 1 by 2a into e power minus a mod t Fourier transform is 1 divided by a square plus omega square. So I know the inverse Fourier transform of this one, which is 1 by, so first we should know the inverse Fourier transform of both the functions. Okay, it is 1 by 2a. What is a here? A is 2 here, a is 2 here. So 1 by 2a is 1 by 4 into e power minus 2 mod. That is the inverse Fourier transform of this one. So how about this one? For this function, inverse Fourier transform is 1 by 2a, which is 1 by 10 into e power minus 5 mod. So what is the inverse Fourier transform for this one? It is the inverse Fourier transform for this one is whatever functions we have. The Fourier transform of this function, inverse Fourier transform of this function is 1 by 4 into e power minus 2 mod t. Convolution becomes multiplication in time domain. So inverse Fourier transform of this function is 1 by 10 into e power minus 5 mod. I think we can simplify this further. 1 by 40 into e power minus mod t, you can take it common, it becomes minus 7 mod t. See the result, how simple it looks like. The result is looking very, very simple, just by using the convolution properties. So remember, understand this. Whatever functions look very complicated, with the help of properties, you can analyze them in a much easier way, in shorter duration of time. Okay. Right. Fourier transform, Laplace transform, these transform techniques, they are all the technique in learning these techniques, learning these topics well is to understand the properties correctly and to get the idea. When you see a problem, to get the idea of what property should I use. Getting that idea is very important. So how will you get the idea? The proper practice and remembering from reference points. So whenever I see this kind of function, whenever I see squaring, how will I get squaring? Differentiation. So whenever you see squaring, you have to understand that, okay, differentiation property we can apply. Okay. So like that, you'll get the idea with practice, and you have to analyze carefully and observe things carefully. Right, wonderful. So I'll ask you one homework question. One or two. I'm asking you the result of this convolution. What do we mean by convolution of signal? So I'll just explain a little bit. So these are homework questions. You can solve them after the session, and if you're able to solve them, if you are confident of your answers, you can post it in the comment section. Right. So when you convolve two signals, convolution is like a mathematical operation, similar to differentiation, integration. Similar to that, convolution is also another mathematical operation. So if those two signals are being convolved, this is the symbol that we use for convolution. The asterisk mark is the symbol that we use for representing convolution operation. So what this means is, when two signals are being convolved, what it means is, the mathematical form I'm writing. Take this function x1 of tau into x2 of t minus tau theta. Limits from minus infinity to plus infinity. So when you're convolving two signals, you're evaluating this integral. Okay. So what is the practical importance of it? So if you take a signal x of t, if you pass through an LTA system, LTA systems have something called impulse response, which we denoted with h of t. And if you want to find the output of the LTA system, how do you find it? We find with the help of convolution. X of t convolution with h of t. Okay, right. So that's it from my side for in today's session. So try these homework questions and post the answers in the comment section. So we'll meet again in tomorrow's session with some other wonderful discussion on Fourier transform, some other topic on Fourier transform we'll discuss in tomorrow session as well. Same time, 8 o'clock. Right. So I've taken already 4 sessions based on Fourier transforms, and I'll be taking 2 more sessions. So if you wish to learn Fourier transforms well, then you can follow all the sessions that I've taken in the last 4 days and the next 2 days also. You can follow all those classes to learn Fourier transform well. Right, guys. That's it from my side. Take care. Good night. Bye bye.